All right, so up until now in the class, every problem we've solved or even when we've talked about different problems, I've always assumed that um, I've just given you the principal stresses somehow, right? But and we've talked about how you can measure or estimate the vertical stress, right, through rules of thumb or through integrating density logs, right? But when it comes to the two horizontal stresses, that's where it gets a little more tricky. It turns out there is a way to measure S3, and I say S3 here because S3, of course, could be the minimum horizontal stress or it could be the vertical stress, right? And in the case that it's a vertical stress, you can measure it with this sort of hydraulic fracturing that we'll talk about next. But you could also you don't necessarily have to do that if it's in fact the vertical stress, right? Because you could also integrate the density logs. So I have a cartoon here of a hydraulic fracture as it's sort of as we currently think about hydraulic fracturing in terms of stimulation. And we're going to talk about that in a couple of, after the exam, essentially, the rest of the class. Well, a significant portion of the last few weeks, we'll be talking about hydraulic fractures for stimulations. But what we're really talking about here is not for stimulations, but as a diagnostic tool, okay? So, hydraulic fractures will grow perpendicular to the minimum horizontal stress, and because that's sort of the minimum energy configuration, right, that it takes, right? So if I have to, if I have a well bore and I increase the pressure in the well bore such that I put the hoop stress into tension, then I can initiate a hydraulic fracture. And then as it grows, as I continue, if I were to continue to pressurize it, as it grows, it's going to grow in a direction that's perpendicular to S3, right? The minimum horizontal S3, the minimum horizontal stress, or possibly the vertical stress. Right? Again, because that's the minimum energy configuration. So knowing that, what direction does it grow in? What is this direction? It's SH max, right? If that's S3, then it's either S vertical or SH min, then that's definitely going to be the maximum horizontal stress, right? So knowing that, we can, so I mean, this is just equation. The hoop stress, so this is the equation for the minimum hoop stress. So remember our sort of stress as a function of theta as we go around the well bore. Looks like this. So if this is the hoop stress, sigma theta theta, here we're talking about vertical wells, right? Then the minimum is this guy, so sigma theta theta. If we set that guy into tension, right? So if this is 0, such that that dips below, the minimum hoop stress dips below 0, then if that exceeds the tensile strength of the rock, which we've written here as T0, but usually we just assume that's 0, right? We talked about the tensile strength of the rock is very, very low, especially compared to the compressive strength. So, if you're in some formation that does have some appreciable tensile strength, 2, 3 MPa, maybe you put it there. But if you don't know, you can just assume it's 0, and so that T0 equals 0. And so then if you put the hoop stress into tension, you can initiate a hydraulic fracture, right? And so that's the equation then that governs that. Right? So what we can do is we can use a hydraulic fracture as a diagnostic tool. So again, these are not hydraulic fractures that are used for stimulation, but rather hydraulic fractures that are used as diagnostic tools to understand what S3 is during the drilling process. Right? And so in fact, you really want these hydraulic fractures to be as small as possible, because you don't want them to induce sort of a lost circulation scenario or influence a lost circulation scenario later. So the tests that we use to do this are most commonly called Leakoff tests. There's other names for them, mini fracs, formation integrity tests, extended Leakoff tests, right? And really, which proper name that you choose for them really has to do with how long you run the test, and I'll talk about that. So what the picture there is an illustration. It's not real data, but rather an illustration of what you would consider to be an extended Leakoff test, right? So normally, you often don't actually run the test out this long, but if you did, this would be called an extended Leakoff test, and we'll walk through what happens, right? So if you this is a function of pressure versus volume of fluid, and if your flow rate's constant, then this could also be time, right? So, because if you're at a constant flow rate, the volume and time are going to just be proportional to one another. So, and of course, as this drawn, this pressure here at time equals 0 is 0. So that implies that this is pressure measured at the wellhead, okay? However, so in order to actually get the real S3, you have to add the column of fluid in the well, okay? You'd have to add the pressure of the column of fluid in the well, which you can easily compute, right? This is a hydrostatic head of that volume of fluid. So these tests are often better done if you can measure them downhole, the pressure downhole. They're more accurate, but as it's drawn here, this would be considered a surface measurement. So if you flow at a constant rate, what you'll see is the pressure will increase linearly. And if you never see a deviation from that linearity, right, and you just stop the test, that would be what we would call a formation integrity test. And all you can say in a formation integrity test, you can't actually say what S3 is, but you can at least bound it, right? So in a formation integrity test, you're just going to pressure up, pressure up, pressure up, pressure up, and then you stop. And you say, well, okay, S3 is greater than wherever I stopped. Okay. That would be a formation integrity test. At some point, though, if you continue to pressure, if you continue to pump fluid, you're going to see a distinct kink in the curve, in the pressure time curve, pressure volume curve there. And the place where these two curves intersect is called the Leakoff point, the LOP, the Leakoff point. And so what has happened here is you've initiated a hydraulic fracture. So when you have a constant, when all you're doing is pumping fluid into a constant volume, being the wellbore, the pressure is just going to increase linearly, right? But eventually, when you initiate a hydraulic fracture, you're going to get some kink in the curve because now the volume has increased, and therefore you're going to you have a larger volume, so you're going to be pressuring up at a different rate. Okay. Now, and a lot of tests are only done to this point, right? So this would be just called a Leakoff test or a mini frac. And so a lot of tests, you'd only perform the test to this point, right? So you just pressure up, see that kink in the curve, and stop the test, and go back to drilling, go back to work. However, if you do continue to pressure up beyond that, then eventually, at some point, you're going to see a maximum in the pressure time curve, and it'll drop, okay? And this is called the FBP, the formation breakdown point. So the maximum in that curve is called the pressure formation breakdown point. And what's happening there is now you are propagating a stable hydraulic fracture faster than your pumps can run. Right? So your pumps can't fill that hydraulic fracture as fast as it can move, right? As fast as it can propagate, and that's why you see the pressure drop. Right? Because now you're increasing the volume faster than the pumps can fill it up. And so then eventually, when you'll see the pressure drop, and you'll reach this point where you have this kind of plateau area, and that's called the pressure at which you see that plateau is called the formation propagation pressure, the FPP, the formation propagation pressure. Okay. And so this is the pressure at which you're growing a stable hydraulic fracture. The other day we talked a little bit about the mechanics of hydraulic fracturing, and if you remember, what I said is that when you have short fractures, then you have this sort of you have to take into consideration the crack tip mechanics, right? In that in this thing called the stress intensity factor, right? We're going to talk more about that when we discuss hydraulic fracture for stimulation. But eventually, when you reach sort of longer fractures, the influence of the stress intensity factor decays with like a square root of length, so it decays quite a bit, and then it's just the net pressure sort of dominates whether the fracture is going to grow or not. Net pressure being the difference in the S3 and the pressure. Yeah.
Do you have like a rough estimate of how much it would cost if we're drilling with like oil-based mud and using it to do fractures, like if all the way through?
You mean if you had to actually take corrective actions because of lost circulation? Yeah, it's a big cost. I mean, I don't really know how to answer that. I mean, it depends on what kind of corrective action. You might have to set casing. You might have to deviate the well, and just depending on what you have to do, it really just depends on time, right? How long it takes to fix it, and the cost is time. I mean, if you're talking about ultra deep water, it's $2 million a day, right? So if it costs you a day, that's $2 million. Right? So yeah, it just depends. It depends on it's hard to answer without knowing more details. Right? So in the event that, say you're doing classical hydraulic fracturing in an open hole well that's not cased with a very low viscosity fluid, or a low viscosity fluid, slick water, right? In that case, it's almost certain that the fracture propagation pressure and the Leakoff point are going to be almost identical to one another. And so that's one of the reasons that the tests aren't often done this far out, is because it's a redundant measurement, right? To understand the fracture propagation pressure and the Leakoff point. So they're often only done to here and then stopped, because it's redundant to take it out this long. However, the reason they may differ is because so that, again, what I said was in open hole wells with high viscosity fluid, right? If you're pumping these fracs through casing, through perforated casing, however, that's a different story, because you have a lot of tortuosity and sort of viscous effects of the pumping fluid. It can be compounded by pumping a high viscosity fluid through perforations, which could cause your Leakoff point to be higher than the actual S3 value, right? Because here, by this time, you've gotten to your sort of fracture propagation pressure. Your fractures are much longer, your volumes are larger, and any sort of small deviations. I mean, obviously you're still pumping through fractures, but all of that kind of effects would have equilibrated to some extent by then, and your fracture propagation pressure will be a better indication of the real value of S3. Okay. Yeah. It really, it just depends. It depends on what your objectives are. I mean, it depends on how wide your mud windows are, how you know, if you have another well nearby that you believe to be representative, you might not do one at all because you've already drilled through there, right? So it really just depends on where you're drilling and what, you know, sort of what your objectives are. Yeah. So the very best estimate, though, would be if you ran it out, and again, this would be what's really called an extended leak-off test, is if you shut in the pumps, when the point at which you shut in the pumps is called the ISIP, the initial shut-in pressure, right? So if you shut in the pumps and quit propagating the fractures, okay, you have now a propped, you know, a hydraulic fracture that's held open by the pressure of the fluid that's in it. But that fluid that's in it is going to leak off into the formation. It can happen very slowly in a tight formation like a shell, to the extent that it could actually take several hours or maybe even days. It could be held open, right? But nevertheless, you have fluid in there that's going to leak off into the formation, and the moment that the fracture closes, right, that's the best estimate to S3 because that's when the system is truly in equilibrium, right? When, you know, the instant that the fracture closes is the point where the pressure inside and the vertical, you know, the S3, the minimum horizontal stress pushing against it are truly in equilibrium, right? And so that's called the fracture closure pressure, and that's somewhere down this curve, right? Somewhere down this curve, and we'll talk about where down that curve in another slide or two, right? So somewhere down this curve, the instant at which the fracture closes is called the fracture closure pressure, and that's your best estimate to S3, okay? So again, what?
On that graph, like, find out which one it is.
I'll show you in just a second. So I'll show you one technique. There's actually, I mean, this is still a very relevant research topic in determining exactly when this is, because the problem is the fractures, when you create them, right, they have apertures, and, you know, it's an irregular, you know, it has roughness, has some surface roughness, and if there's any shearing at all, I mean, you can't expect that the fracture you open is just going to perfectly close, right? I mean, anybody that's sort of broken anything in their life, they break a piece of ceramic or something and try to stick it back together, it never goes back perfectly, right? You can never get the crack that you created to disappear, and that's because there's always some material loss and asperities. And then think about if you sheared it at all, such that now they're not even perfectly aligned anymore. And so all of these things have a very small effect to the tune of, you know, a few. It could cause you to change your interpretation of the results by an MPa or two, you know, a megapascal or two, and depending on how accurate you want to be. Okay. But yeah, I'll show you one technique for finding when the fracture closure pressure again. So again, if you're open hole well, high viscosity fluids, particularly in a you know, not extremely tight formation where you're going to have rapid leak off, then your leak off point, your fracture propagation pressure, and your fracture closure pressure would all be roughly the same value, and then they would be redundant. So in those cases, it's unlikely the test would even be run that far, right? Because it's all slowing you down, taking time to do this. Okay. So yeah, I'll just, you know, that was a cartoon. This is just to show that, this is just to show some real data, right? So down here, you have, these are your flow rates, which, you know, in the first one, there's some oscillations in the flow rate, but, you know, if you sort of average it out, it's roughly constant. And then the well shut in, and then the other one is the pressure. So over here on this axis is your flow rate, and this axis is the pressure. This is versus time, and since they were near constant flow rates, this is also volume of fluid. But you see a curve that is pretty similar to the cartoon picture, right? It's a little bit difficult to see where the exact sort of leak-off point or change in inflection is. And in this case, you know, it certainly appears to be different than the fracture propagation pressure. You actually don't need to, once this flattens out in this part of the curve, you don't actually need to propagate the fracture very long, because it's never going to, well, it's not going to change too much. So you can, once it flattens out, then you can go ahead and shut in the pumps and try to get your, oh, I'm sorry. I was looking at the wrong part. Once this part flattens out, right, this is your fracture propagation pressure, and then you go ahead and shut in the pumps, and you see this decay due to leak off. Yeah, so, you know, if I had to pick it in this plot, just, you know, without, obviously you'd want to use some better tools than eyeballing it. Use some computational tools to pick the best inflection point. But yeah, I mean, it's somewhere, your leak off point's probably somewhere here, your formation breakdown pressure there, your fracture propagation pressure there, and then I really can't tell where the fracture closure pressure is yet. Okay, so one way to do it though is, so this is a zoomed in look at that. Let's go back a slide. What we're looking at here is sort of what we're looking at here is this part of these curves for the 2 cycles that were ran here. And they're plotted in 2 different ways. The first one, right, so the top 2 plots are the first cycle. The second 2 plots are the second cycle. And the only difference between the 2 is, you know, this is pressure as a function of time, and this is pressure as a function of square root of time. And if you plot it as a function of square root of time, particularly in this second cycle, you can see a distinct kink in the curve. Right? And the reason you plot it as the square root of time is because this process of leak-off is a diffusive process, right? Diffusion. And diffusion is governed by Brownian motion, right? So, you know, Brownian motion is just, mathematically you can model as a random walk, right? Just particle that just takes a fixed size step in a random direction and walks around, right? And if you do enough of these, then you get a Gaussian distribution of sort of particle distances. And if you were to check, you know, statistically, if you were to follow any one of those random walking particles, you would see that its distance from its origin is proportional to the square root of time. Okay, and so anytime you have a diffusive process, any tracer particle is mean distance from where it started is going to be proportional to the square root of time. And so that's the idea behind plotting versus the square root of time. And when you do that, you get at least certainly in the second cycle, you get a pretty clear kink, an inflection point in the curve. And that is your fracture closure pressure, your FCP. There's also another type of test called a step rate test, which in principle is applied in the same way that a leak-off test is, except now you vary the flow rate. So you pump at a constant rate, and then you increase the rate, and then you increase the rate, and then you increase the rate in steps. And if you're pumping into a constant volume, then that increase is going to cause a linear increase in pressure, right? It'll always just increase in pressure linearly. And then once you continue to do this over time, then you'll get basically a distinct kink in this curve, and again, that's from the volume change associated with propagating a fracture away. And where those two curves meet would be your S3. Right? So that's another way to do this type of test. We call that a step rate test. So I think I'll stop there.